Okay, let's give you guys some practice. So cos x squared looks something like this. So integrate this from 0 to 1, from 0 to 1. So basically, work out this area here. Work out this area here. But the thing is, you don't know how to integrate this. So you need to turn it into a series and then integrate each individual term of the series. The question is, how many terms do I need? How many terms do I need in order to get this area to be within this level, of accuracy? Okay, so work out the number of terms I will need in order to get this area to be within this level of accuracy. So press pause and have a go. Okay, so to do this, let's just zoom into this bit here, the cos x. So zooming in would look like this. Now we need to turn this into a series. So turning into a series, imagine this as being x squared. So you would then put it into here. So this would be x squared to the power of 2n to the power of 2n. So now simply this times this, that would be 4n. So cos x squared expressed as a series is given by this. So cos x squared expressed as a series is given by this. But the thing is, we want to integrate this, but we don't know how to integrate this. So let's integrate the series. Well, integrating the series will then give you this, because if you think about it, hang on, if you try and integrate x squared, it would be this. So if you integrate a series, this thing here gets added by 1, so it would be 4n plus 1. But then you've got to divide it divided by the exact same thing. So divided by the exact same thing, 4n plus 1. Well, we've done this before. If you integrate this, it will then give you this, and then we need to evaluate it from 0 to 1. We need to evaluate it from 0 to 1. So when you get to this stage here, in your mind, visualize it as one fraction, take away another fraction, plus another fraction, take away another fraction, and so on. So you will need to do this. Put 1 into here, put 1 into here, put 1 into here, put 1 into here, and then take away, put 0 into here, put 0 into here, put 0 into here, and so on. But the thing is, when you put 0 into here, when you put 0 into here, 0 to the power of this thing would be 0, and then times this would be 0. The whole thing here would be 0. So when you put 0 into here, it would be 0. When you put 0 into here, this thing would be 0. When you put 0 into here, it would be 0. So you're taking away 0. And then when you put 1 into here, that would be you putting 1 into this thing here. So this would be 1 to the power of whatever. It would be 1. So that would be 1 here. When you put 1 into here, it would be you putting 1 into it. The point is, when you put 1 into here, put 1 into here, you put 1 into here, each individual term, this thing here will always be 1, because it will be, when you put 1 into here, it will be 1 to the power of whatever. 1 to the power of whatever is always 1. So this thing here will always be 1. Well, anyway, we've done this before. Evaluate this. That will then give you this thing here. So when you try and integrate this from 0 to 1, this whole thing here is given by this. Now, because we were trying to work out the number of terms needed, we need to think about the remainder. Remember, the original question was, how many terms do I need in order to get the area to be within some level of accuracy? Well, in order for you to work out the number of terms needed, you would need to think about the remainder. Now, in order for you to make use of the remainder, you would need to show that this is an alternating series and it converges. So our next step is to show that this is an alternating series and it converges. Then we can think about the remainder. So next step. So let's carry out the next step. So the next step is to show that this is an alternating series and it converges. So the routine is always the same. Discard the alternating components. Concentrate on the UN. Show that all the UNs are positive. In this case, it's positive. Show that it's non-increasing. I'm whizzing through this, so I'm assuming you can do all three here. well, the limit actually heads towards 0. So I'm assuming you can do these 3 steps. So now we've got an alternating series that converge. Well, whenever you have an alternating series that converge, then you can be sure that the remainder will be less than or equal to this one specific term here. So this is your UN, it will be the next term. The remainder will always be less than or equal to the next term. So if you go back here, the remainder will always be less than the next term. So the next term will be n plus 1. So put this into this n here. Put n plus, the next term will be n plus 1. Put it into this n here. So this whole thing here will then become, well, the next term will be, hang on. So if you look at this, you've got 2 times n factorial. So this bit here will be 2n plus 2. 2n plus 2. And then this thing here will be 4n, and then you've got 4 here, and then plus 1, so it'll be plus 5. So this whole thing here will be 4n plus 5. That's where this 4n plus 5 and 2n plus 2 and so on. Okay, so your remainder will be less than or equal to this to the next term here. Okay, but because we are trying to work out the number of terms needed, so we require our remainder to be strictly less than 0.001. Remember, this was given right from the start of the video. So now we require our remainder to be strictly less than this. So now take the reciprocal both sides. That will then give us this. So we require this to be bigger than 10,000. So because of this factorial thing, we don't have an elegant way of solving this. So we have to guess. So when n equals 2, this whole thing here, when n equals 2, this whole thing here equals this. Well, this thing here is not bigger than 10,000. So when n equals 2, it's no good. When n equals 3, this whole thing here is this. Well, this thing here is bigger than 10,000. So this is good. So when n equals 3, meaning we would need 4 terms. We would need 4 terms. 1, 2, 3, 4. Now we can be sure that the area is within our level of accuracy. Okay.